I'm thanking the organizers for giving me the opportunity to talk today. And I'm going to talk about how to directly compute reduced density matrices for open quantum systems with influence functionals. And since we have only 50 minutes, I'm going to sketch everything. So more details are, of course, in my corresponding paper. So first of all, what is an open quantum system? I mean, we already heard about it today, but it's basically a quantum system that is interacting with some surrounding environment. I denoted the system by S here, and the environment by E. Often one assumes that the system and environment are weakly interacting, and usually one assumes that the system is influenced by the environment much more than the system influences the environment. And examples for open quantum systems are atoms and laser fields, for example, or you could consider a test particle that is moving in a gravitational field, and then your test particle is the system, and the gravitational field is the environment influencing your quantum system. All right, and a common way of describing such an open system is via a reduced density operator. You obtain the reduced density operator by tracing out the environmental degrees of freedom of the density operator that contains information of system and environment. And you can project your density operator in some basis to obtain reduced density matrices. And the time evolution of these reduced density matrices is described by quantum master equations. And the issue with such master equations is that they are sometimes intricate to solve. So it would be nice to have a way of directly computing your reduced density matrix without actually having to think about master equations. So what am I going to talk about today? This is the following. First of all I'm going to talk about will be around this simple example here. So I'm considering a system which is a real scalar field phi, and I have another real scalar field chi as my environment. In this article from a couple of years ago, we introduced formalism, its first principle based and very practicable, in order to derive a quantum master equation for such a toy model, but generally also for other systems and environments, of course, in a physically or experimentally relevant basis, namely the momentum basis. And we had applications to quantum experiments in mind. For example, if you consider atom interferometry, you could put your atom into a momentum superposition, and then you could use our formalism to calculate how it's evolving. Right, and the whole idea is based on different tools. They are taken from thermo field dynamics, the Schwinger-Keldyh formalism, and the Feynman-Vernon influence functional. Some of them you have already heard about today, but I will talk about them a little bit more in detail later. And recently Mario Pitchman and I, we put out this paper here, and there we use the same formalism, but for directly computing the reduced density matrix without even having to think about master equations. So you can calculate the density matrix, and you don't even have to write down a master equation to get it directly in a momentum basis in this case, but you could also think about other bases, of course. Right. So let's talk about density matrices. Again, we have a density operator as a reduced one for phi. It's just a trace of, with respect to chi of the full density operator. And I restrict myself now to the single particle subspace. So I say that the only density matrix that is contributing to my density operator is the one that describes the single particle in superposition, in a momentum superposition. Other occupations are actually to be found in my paper. And as usual, the density matrix is defined in this way. And I introduce some shorthand notations for the integrals. So what I want to find now is an expression for my density matrix at time t in terms of the density matrix at time 0. So I put in some initial data that I know as an experimentalist, for example, and then I find out, okay, my density matrix looks at time t in this way. Yeah, so I could see the coherence and things like that. Okay, so what is already known? I mean, from the literature, for example, from Professor Hu's book, we find that the density functional in the field basis can be given in this way. It's defined in the Schwinger-Keldyh closed time path formalism. So you have phi plus and phi minus fields. As you know, in the Schwinger-Keldyh path integrals formalism, you have a positive time branch that is moving in the positive time direction from the initial time to the final time. And you have a path that goes backwards from the final time to the initial time, so that such that you have a closed time path. And this phi plus minus t indicates the dependence on both phi plus and phi minus at the time t. So, and obviously phi plus is a field living on the positive time branch, and phi minus is a field living on the negative time branch. So this is already known, this is in the literature. And we also know from the literature how this density matrix in this, or this functional in this basis is evolving. We have this path integral expression here. This is just a free action of phi. This is the itself interaction of phi. And this is the so-called Feynman-Vernon influence functional, which captures all the information of how the environment influences the system, while ignoring actually how the environment itself is evolving in some sense. So you forget about the environmental degrees of freedom and capture all the effects of the environment on the system in this single term. Right, and I introduced this wide head notation here in order to have a different way of denoting that my actions here depend on phi plus and phi minus at the same way, at the same time. And the Feynman-Vernon influence function in this case is given in terms of this influence action. And I can rewrite this in terms of an expectation value with respect to chi. So I trace out some chi degrees of freedom here. And I have the self-interaction for chi, and I have an interaction between phi and chi. So the question is now, how do I actually get a similar expression in momentum basis? This is not that obvious. So let's move to the quantum Lie equation. This is very well known. It's the equation of motion for your density operator. And we know the general solution for this is this expression. But from here, at least for me, it's directly obvious how to move to the momentum picture there. So it's a little bit tricky. So let's do something better. We actually move to thermo field dynamics, which allows us to re-express the quantum Lie equation in a nicer form. Thermo field dynamics is, in some sense, an algebraic formulation of the Schwinger-Keldyh formalism. You're working in a double Hilbert space here. So you have H plus times H minus. H plus is the Hilbert space corresponding to the positive time branch of the Schwinger-Keldyh contour, and H minus correspondingly corresponds to the negative time branch. And you can define operators on these two Hilbert spaces. The plus one just lets you act with the ordinary operator on the plus space times the unit operator on the negative space. But if you consider an operator with a minus, one that acts on the negative space, then you actually have to consider time inversion. You can also define a vacuum state and introduce this nice double cat notation. And of course, you can also have creators and annihilators as always, but of course, you have to distinguish between plus and minus creators and annihilators. Right. So in addition, you can define this one state here, which allows you to take traces or formulate traces in thermo field dynamics. So if you have the expectation value of an operator, you can, of course, write it as a trace of the operator with the density operator. And this is then given in thermo field dynamics as this term here on the right-hand side. And using all this technology, you can actually write the quantum Lie equation for the reduced density matrix, for the reduced density operator in the interaction picture in the following form, where the two Hamiltonians are the following. The first one here is corresponds to the self-interaction of phi, and the second one corresponds to the influence action that I showed you earlier. And this has a very easy solution. You just find this expression, and these two Hamiltonians that I have here, they both fulfill this type of definition. And so they also have such a wide head in case it's hard to see. Right. Okay. So as I said, we want a formula for the density matrix and momentum basis at time t. We start with the trace and formulate it in thermo field dynamics. You see on the right-hand side of this trace, we have this row plus times the one state. This we already know from here. Exactly, we already have the solution. We can just plug it in. And then we pull out all the creators and annihilators, replace them by field operators, and introduce this nice shorthand notation here just for information. And we then find such an expression that looks like an LSZ reduction, but it still contains this 4-point function here. And we just use this known relation between action operator and Hamiltonian operator. And translate this then into path integrals such that we find this final formula here. So this is a path integral expression now that allows me to directly compute the reduced density element on the left-hand side in terms of the reduced density matrix on the right-hand side at time 0. You see, we again have the Feynman-Vernon influence function in here. We can evaluate this perturbatively and just calculate our left-hand side. That's actually much more straightforward than it might look like at the first glance. And you can take the same derivation and extrapolate it for other numbers of particles. So you can investigate how, if you start with a superposition of one particle, how the single particle element not in superposition evolves, for example. So in this way, you can observe decoherence and things like that. So we can discuss any numbers of particles, basically. Right, so the summary, so we found a practicable formula for directly computing reduced density matrix elements in an experimentally relevant basis, so we can apply it to quantum experiments. And as an outlook, one problem that pops up in this context, if one doesn't talk about an effective theory at least, is that you have to renormalize, and the renormalization here is a little bit trickier because, as always, or as is very common in this area, you assume that your system and environment are separated at the initial time. And this causes the system to actually be a quenched system, and such quenched systems show time-dependent singularities. So this means that your singularities actually are not existing at the initial time, and they might even vanish during time evolution because you have oscillations and so on. So you actually need counter terms that take care of this. And yeah, this renormalization needs to be studied in more detail, and that's very interesting since it could also or will also be applicable to theories that have non-trivial dependencies on space-time or space-time. So yeah, that's it.
Okay, thanks for your talk. Very nice talk. And well, it's time for questions or remarks. Any question? Well, there is one. Thomas, you can ask.
Hi, Christian. Thank you very much for this nice talk. Can you hear me well?
Yeah.
I was. How much your final result depend on the fact that you use thermal field dynamics? So I guess at some point some thermality assumption for the environment.
Oh, no, there's no thermality. The thermal field dynamics is just a mathematical framework to guide this whole thing, because it's not directly obvious how to get from the path integral formalism to where actually you want to go. So there might be a more direct way, but there's no assumption about thermality here. It's just this double. You could maybe even forget about thermal field dynamics and call it differently. You know, sometimes you find this real space formalism or something like this. But you could, of course, also include thermal effects in here as in the paper that I have now. I don't consider them, but it's simple to put them in. So, but there's no assumption in this regard yet.
Okay, that's great. Thank you very much.